Welcome to VFD Vibes, your place for all things related to variable frequency drives. If you're interested in how to make things turn, or manufacturing technology in general, then this is the place for you. When it comes to power systems, everyone's heard of harmonics, but few truly understand what they are, why they matter, or how to deal with them. Misunderstandings can lead to overheating equipment, unexpected shutdowns, and costly design mistakes. This is episode 9 of VFD Vibes, Harmonic Headache, where we're clearing up that confusion. I'm your host, Greg Wichman, and joining me is Jordan Engel, product manager for Yaskawa's low harmonic matrix drives. Together, we'll break down what harmonics are, how VFDs contribute to them, and the most effective ways to keep them in check. Let's get into it. So thanks for being here today, Jordan.
Yeah, hello, Greg, and thank you for having me.
I'm going to dive right in, and when we talk about harmonics in a power system, what are we actually dealing with? Can you define them in simple terms?
So I guess we'll start by discussing what we mean when we say power system. When we refer to the power system, this is how energy is distributed to our homes, our businesses, and our factories, electrical energy. And this electrical energy is in the form of AC current. It's the result of an AC voltage, which is alternating polarity, at a rate of 60 hertz, which means 60 times a second, your waveform is repeating its cycle. And this waveform, if you were to plot these changing voltages on a screen, is a nice sinusoidal waveform. It's smooth and clean, and if you connect a load, such as an incandescent light or just an electric motor or an electric heater, this waveform will remain clean and smooth. And that's what we talk about in a power system in an ideal setting. When we start talking about harmonics, harmonics are higher frequency currents in addition to that 60 hertz waveform that are the result of what we call a nonlinear load. So a nonlinear load is drawing current which is not sinusoidal in nature. So when you have nonlinear current draw, you have the formation of harmonic currents, and these can cause problems in your electrical system. So to start, I would like to use an analogy to describe harmonics so that the listeners can use their imagination on a subject that we can all relate to.
I appreciate that. I realize we don't have slides, we don't have visual aids, so that was a great description. But for those that maybe haven't pictured this in their career in a real world setting before.
Right, so a good visual, let's imagine that we have a large body of water like the Great Lake, Michigan, or the ocean, and that there's wave action, and that these waves are nice, smooth, rolling waves. And offshore you have anchored a raft for swimmers to swim out to and jump onto and jump off of. And as it relates to a power system, you could look at these waves as the energy source, the waves of water, and the raft, which is being lifted and lowered by these waves, as the load. So you have a group of people swim out to this raft, and they're standing on the raft. The raft is going up and down, consuming some energy from the moving water, and it's largely what we would call a linear load. It's not disturbing any of the water around it. It's just taking some of that energy and moving along with the water. Now, what if, for example, everyone on the raft, kids decide to play games, they decide to all jump up in the air at once and land their feet back down on the raft, everybody jumping in unison? Well, that would be a good example of the raft transitioning to a nonlinear load. And what would happen? Well, the raft would still go up and down with the waves. Their jumping action wouldn't change any of that. But around the raft, you would notice every time they jump, a bunch of little waves would radiate outward from the raft. Waves that are higher in frequency, so they're, shorter distances between the peaks and the troughs compared to the surrounding water. And, that would be the extent of it. Okay, well, that's an analogy for a small nonlinear load on a large electrical distribution system. No real consequence, but something that anyone could observe. Let's take that example and pivot to perhaps a swimming pool. It's difficult to imagine smooth rolling waves in a swimming pool with a float or a raft with one or more people going up and down in the pool, but let's carry that over from our lake or ocean example and just imagine that it was that way. Okay, so in a swimming pool, if that same individual or group of people jumped up and down on this raft that's moving with the rolling wave action, what would happen? Well, you would still have the waves radiate away from the float or the raft, but instead of just disappearing into the distance and not causing any consequence, these waves would reflect off the side of the pool and other swimmers would be disturbed and, it would really disrupt the water.
You might splash some water out of the pool, for example.
Yeah, you might get someone wet that's got their laptop or phone or perhaps even reading a book. That analogy is similar to a nonlinear load on an electrical system that's smaller in size. And this is how we pivot to how harmonics impact an electrical distribution system.
What I'm understanding is when a load is following the voltage from the power system smoothly, the raft going up and down, there's no issue. But certain types of devices in our modern world, anything with switching electronics, such as a drive, also computer power supplies, modern TVs, things like that, they start to cause these little ripples in the way that they draw power out of the system. Why we don't care about this at home, for example, is a TV is a very small load compared to the overall draw of our house. Likewise, if you had a 1 horsepower, or even a handful of 1 horsepower drives in a factory, it's a small percentage of the power consumed. Where we really need to start looking out for harmonics is when that percentage of power consumed by nonlinear loads starts to get large in comparison to the linear loads. So maybe I have a couple 500 horsepower motors in my medium-sized factory. Now I have to actually start thinking about what effect they would have.
Yeah, absolutely, Greg. You make a couple of good points. The first point that you made was, well, there's a number of loads, a number of devices that we connect to our power supply, which are nonlinear in nature. And as technology has evolved, you may hear the term switching power supply. It's an efficient design of a power supply. But one consequence is that switching power supplies don't draw linear current, and as a result, contribute to the formation of harmonic currents in our electrical distribution network. So examples of nonlinear loads with switching supplies are variable frequency drives, the business that me and Greg are in, LED lighting, computer power supplies, EV charging. All of these applications involve loads which are not linear in nature.
Why should I care about these harmonics? Now we kind of have a visual of how they occur. We know that size in relation to other loads around us matters. When that nonlinear load starts to get big enough to have an effect on the system, what are the negative effects? Or again, why do we care?
Well, some harmonic content, some harmonic currents are okay. They generally won't cause a problem. But if you start having excessive harmonic currents, well, you have a number of potential consequences. The first and foremost is probably voltage distortion. So your system voltage is what all the other devices on that particular system see. And if excessive harmonic currents are distorting that voltage, you're impacting the power quality to other devices connected on your network. So if you have excessive harmonic content, certain lights may not turn on, computers or electronic devices may malfunction or throw errors, and in serious cases, you could have some damage. You can have unwanted resonance, instability in your electrical network where you may see overvoltage conditions appear out of nowhere. That can also happen if you have too many harmonic currents.
And I would assume just because in general, when we tend to be inefficient with electronics, they tend to generate more heat. So could there be heat problems, or could this be an added cost in a design because we require additional cooling or oversizing of components like transformers?
Oh, absolutely. Additional harmonic currents, which are presented upstream of your nonlinear load. So if you have a variable frequency drive, for example, upstream of that drive, you'll have branch circuit protection, you'll have transformers, you'll have wiring. All of the conductors will operate in a less efficient manner, meaning release more heat, and overall the system efficiency will be reduced.
When you talk about traveling upstream, though, the harmonics we're talking about today are different than when people talk about EMC, correct?
Oh, yeah, Greg, you bring up a different subject entirely, and this pertains to variable frequency drives and just how a drive is designed. The nonlinear current draw and the switching we're referring to when we talk about a switching power supply, we're talking about the front end, the input side of a VFD. There's low-speed switches in the converter section, which is rectifying AC voltage to DC voltage for the internal DC bus. Those switches are what's causing harmonic currents. Unrelated, on the output section of the drive, there's another set of switches. This is called the inverter section of the drive, and it uses what are called IGBTs, insulated gate bipolar junction transistors, to rapidly switch the output of the drive to mimic an AC waveform of variable frequency, variable voltage, using very fast pulses of DC voltage. This high-speed switching can be conducted upstream of the drive, EMC, conducted emissions, and then there's radiated emissions, which go from the drive to the motor along the motor leads. Those are radiated EMC emissions. This type of interference is very high frequency. It's in the radio frequency range. You're talking about tens of thousands of hertz, and generally is different than the harmonic disturbances we've talked about so far. And it's handled separately. In terms of radiated emissions for EMC, you practice good wiring practices. If EMC is being introduced upstream of the drive, there's options such as specific EMC filters which can filter out that content. But often customers have confused EMC interference with a harmonics issue.
I don't want to take us down a second rabbit hole. We've already got a complex topic for the day. But I do want our listeners to know that there is a difference between the input or current and voltage harmonics we're talking about versus EMC. And you've probably heard of a term, an EMC filter. That is specifically for that issue. As we go along in this episode, we're going to talk about some of the mitigation strategies for the harmonics that we're talking about. So we know the harmonics can have a negative effect on things in our own plant. I would imagine, though, that enough harmonics can actually traverse out of your own facility or building and affect your neighbors, for example. So is there a governing body, or how does a power company or someone make sure that you're being a good neighbor and taking care of your power and not affecting other people that share the grid with you?
That's a real good point, Greg. Yes, your harmonic content can pollute the power you have within a facility. And if that power source is shared with other customers, it can impact them as well. And harmonic content ultimately makes it upstream to the electrical utility. There really isn't one governing body. Different utilities have different policies. My background in this business includes an amount of time in field sales, so I actually, made customer visits. And some customers said, hey, my electrical utility is telling me that I either cannot make it any worse, the existing harmonic content that I'm introducing into the network, or I have to improve it, or there could be financial penalties. IEEE, the Institute for Electrical and Electronics Engineers, has what has traditionally been referred to as a guideline, 519, and is transitioning more or less to a standard. There's a number of revisions of IEEE 519 from 1992, 2014, and then the most recent revision, 2022, that outlines parameters for your electrical system in terms of how much THDI, that is total harmonic distorted current, and THDV, that's total harmonic distorted voltage, is considered acceptable.
So if you reflect a little more back on your sales days, you said you've come across customers that have had this as a problem. Do you have any specific examples you can share with us?
Well, that's an interesting question, Greg.
Without throwing anyone under the bus, of course. No names.
Right. We'll keep this anonymous. But some customers, as I previously mentioned, had been engaged by their utility that harmonic content was excessive. Now, in those instances, I was unaware of any adverse consequences or effects of these harmonic currents, except that somebody measured them and found that they were out of compliance. There are, however, a couple of instances, one in particular, where a customer had an issue with a variable frequency drive that was producing too much harmonic content. And this was a pump station in a somewhat of a residential area in New England, and they had a 75 horsepower drive connected to a 75 horsepower pump in a pump house, so to speak. And it had run this way for a number of years. They did an upgrade in the fall of 2023 in which the lighting was changed from fluorescent lighting to LED lighting, and the instrumentation was digitized, and just a general upgrade to the equipment. And this pump station ran throughout the winter without any issue. And come springtime, this customer reached out to me and said, "Hey, when I'm running my pump, my LED lights won't turn on. And my flow meter instrumentation is producing erroneous readings." And I thought, well, that's interesting. And so I made a sales visit. And this was a particularly interesting visit because this pump station had run for years. And then in the previous fall had been upgraded, and it ran throughout the winter. And this happened right about April. And I'm surveying the facility and noticed there was a large amount of electric heating installed. And I asked if the heating had just been shut off, and the customer said yes. Well, to get to the close of this story is that the facility always had a harmonics issue. And prior to the equipment upgrade, the old equipment wasn't sensitive enough to the voltage distortions. It operated fine. After the upgrade, LED lighting with sensitive startup circuitry and flow meters that were more sensitive to voltage variations were installed, but they ran through the winter without issue. In the springtime, the electric heating was shut off, and that's when the customer first saw that they had an issue. Well, it turns out the electric heating actually dampened the voltage distortions. Electric heaters are not a harmonics mitigation tool by any means. However, in this particular case, running the electric heating smoothed out the voltage distortions and allowed equipment to work as it should. As soon as the electric heating was shut off, the harmonic currents and the resulting voltage distortions presented themselves, and the LED lights wouldn't turn on, and the instrumentation didn't function correctly. So this customer had to install additional harmonic mitigation to make the system work under all conditions.
Yeah, I like that story because it makes you think outside the box. A lot of times you think that there has to be a big change for this harmonic issue to show up. And you talk about the heaters. Obviously, they're not there to mitigate harmonics. They're there to heat the building. But when we talked about the pool analogy, when the heaters are on, the draw of the whole facility is larger. So it makes the pool bigger, essentially. The draw from the motor is a smaller percentage of the total power draw from the facility, right?
Well, the heating provided a dampening effect, which brings us to when you're doing a harmonic analysis, an estimation, for example, if you're looking at a potential new facility and you have your one-line diagram showing your distribution transformer and all the loads connected to it, it's not just the drives that matter or your nonlinear loads. The size and electrical characteristics of your distribution transformer, in addition to other loads that may be linear in nature connected to this transformer, will all impact the total harmonic performance of the system.
The other thing that really made me perk up was just the thought of new electronics. And in my career, I've done a lot with inputs and outputs, signals to PLCs, as well as industrial networks. And what are we always trying to do is increase speed, increase throughput. What tends to happen is your wire sizes shrink. You have more twisted pairs. The field bus networks of a couple decades ago were extremely robust. They were also extremely slow. So as we have new instrumentation that's now sending 100 pieces of data instead of 10, and the network is much faster, it's much more sensitive to these types of transients in our power system. And so in a facility where maybe you don't even do a VFD upgrade, you just do a electronics upgrade, again, you might have had a harmonics problem all along, but you never noticed it. Now all of a sudden it's rearing its ugly head because you've got more sensitive equipment.
Absolutely, Greg. And this is why it's always good to consult with people in the industry that have specific knowledge of this phenomenon and what's happening, because to engage in an investigation without any of this background knowledge would be rather mysterious and confusing to most people. And you mentioned environments with varying degrees of technical equipment. You talk about hospitals and laboratories. High-tech laboratories have very sensitive equipment, and the harmonic requirements for these facilities can exceed that of even what IEEE 519 is recommending. So in large measure, the types of loads you have connected to the network also determine just how much mitigation you may or may not need.
And let's circle back in a minute to some of the studies and tools we can use to predict our harmonics, especially if we're making an equipment change or a facility upgrade. But let's take a step back and just kind of talk about general control. We know VFDs bring tremendous energy savings and process control. We don't want to eliminate VFDs, which means we have to make sure that we keep the harmonics in check for IEEE, as well as to extend the life of our own equipment, as well as be a good neighbor on our power system. So what are the most common mitigation strategies for these types of harmonics?
Well, there's a toolbox available, Greg, and thank you for mentioning the subject. When you talk about just a drive with no mitigation, that drive will produce upwards of 90% THDI. That's your total harmonic distorted current.
I want to clarify, you mean a standard 6-pulse drive.
Standard 6-pulse drive, your standard off-the-shelf VFD from Yaskawa or any number of suppliers will perform about the same without any form of mitigation. The first line of defense is to add inductance. So what's inductance? Well, an inductor, which has inductance, is an electrical component that resists changes in current. So in the case of a line reactor, this is a component you put on the input of a drive, and it helps filter out these higher frequency harmonics. There's another component that's similar to a line reactor called a DC bus choke. That is either one or two components, depending on the design. Each drive has a positive and negative rail in the DC bus internally, and unlike a line reactor, which is typically external to the drive, a DC bus choke, or chokes, in the case of two, is an internal component on the DC bus. And again, the reactors, the DC bus chokes, are resisting changes in current. Adding these devices can get your THDI down to anywhere from 32, 33 to upwards of 40%. So you're looking at an improvement by half or more in terms of harmonic performance.
As you explain this, I'm thinking of when your dishwasher or washing machine at home is pulling water and turns off its valve. It turns it off hard. Sometimes you can hear that rattle through your pipes. Oftentimes there's a little arrestor installed to prevent that. And that's kind of how a standard 6-pulse drive pulls its current. Its switches are on and off pretty hard. Versus if I were to turn the faucet on and off by hand, as quick as I think I can be, I can't slam it like a valve. I know the inductance is not controlling the switches, but it is evening out that flow, similar to turning the valve on and off slowly versus it slamming on and off.
Yeah, Greg, that's a great comparison because, these line reactors are essentially softening the blow, so to speak, for this nonlinear current draw. If we go back to the analogy of our kids on the raft floating in the waves going up and down, adding a line reactor would be like telling the kids they could still jump, but instead of landing smack down on the raft with their legs straight, they would bend their knees and squat down as they land on the raft to soften the blow, the impact of them coming back down. So that's what adding inductance essentially does to the front end of a drive in terms of your harmonic performance.
Well, thank you for making a much better analogy than I could and tying it back to our original visualization. But if inductance isn't doing enough for us, what's the next step?
Well, we have a couple of categories of harmonic filters. There's a passive harmonic filter design, and then there's an active design, and they are completely different from one another. A passive harmonic filter is, similar to a line reactor in that it has a line reactor, but it also adds a capacitive component as well. And a passive harmonic filter, the designs do vary, but typically provides a tank or a trap for the harmonic currents to be contained between the filter and the drive. Yeah, they work very well. You can have THDI performance in the 5 to 10% range. The inherent design of a passive harmonic filter, however, does open the possibility of some instability with the VFD, and that there's capacitors inside the VFD on the DC bus, and it may require some changes to advanced parameters within the drives in terms of the internal voltage regulator. An active harmonic filter, however, behaves completely differently. This is a device with semiconductors with switching built in, and what it does is it's connected to the line and it listens for harmonic currents and it injects opposing harmonic currents. So there's a perfect analogy to how an active harmonic filter works is your noise-canceling headphones. How do noise-canceling headphones work? Well, just like I described. You have your headphones on, unwanted noises are coming at you from all sides, and the headphones are listening and producing opposing sounds that effectively cancel out the unwanted noise and create silence. Active harmonic filters can have performance at or under 5% THDI and can be applied at a single point in an electrical network. That simplicity is nice. Often if you're dealing with a situation where a customer has an existing installation and needs to fix a harmonics problem, it can provide an easier solution. One point of harmonics mitigation, however, means that if that active filter faults or fails, you could see a large surge in unwanted harmonic content in your network and thus have problems.
On the passive side, do those tend to be more one-to-one with a drive? And since you said there could be resonance issues, are there guidelines? Do manufacturers tend to have recommended filters for their drives, or does someone you need to reach out to the manufacturer each time you plan to install one?
Well, we'll start by answering your questions, Greg. Yeah, typically a passive harmonic filter is one-to-one, so you will have one for each drive. And either the filter manufacturer can provide guidelines on drives that they've tested or approved to be used with their filters, or you can also consult with the drive manufacturer and cite the particular filter you're looking to use, and often they can provide some guidance on A, if it'll work, or B, if there's a potential issue, what can be done to make it work.
So far, these are kind of, I'll call them add-on or bolt-on solutions. They can be installed with the drive or even in an existing system. Are there other types of drives out there beyond the standard 6-pulse that have better harmonic performance?
Yeah, Greg, so I'll start by discussing some older technology. Our listeners may be familiar with multi-pulse drive packages. These would be 12 or 18 pulse designs, and I use the word package because these aren't standalone drives. A multi-pulse drive package uses a phase-shifting transformer and additional rectifier blocks on the front end of the drive in the converter section to phase shift your incoming voltage so that you reduce your DC bus ripple and you reduce the amount of filtering your bus capacitors need to do, and that improves the harmonic performance by smoothing out that nonlinear current draw on the front end. These multi-pulse drive packages have been around for 30 plus years. They work well, but they are large, and because of the added components, reactors, the phase-shifting transformer, they're generally less efficient.
I know 12 and 18 pulse designs have been around for a long time, and I've also heard that they are mostly being phased out because there is newer, better technology out there. So what are the trends? What is the new technology out there?
Well, there's a couple of ways we can go. First would be what we call an active front-end drive. So I talked earlier, and I think, Greg, you've done some other podcasts on how a drive works, where your AC voltage is converted to a DC voltage in the DC bus, and then that DC voltage is inverted to an output to the motor using IGBTs. So a traditional drive has diodes on the front end, IGBTs on the output side. An active front-end drive has IGBTs on the input side as well as the output side. So the front end has IGBTs, the output section has IGBTs. And by doing this, an active front-end drive is able to actively control the incoming current on the front end. So harmonic currents, nonlinear current, can be interrupted and smoothed out that way. So you have a drive that can perform with 5% or less THDI. These drives, some of them are available in unified packages, but traditionally have been available as in the case of a multi-pulse drive, in a package where you have an inverter module, an active front-end module, the required filtering all in an electrical panel. But some manufacturers have taken the most popular sizes and integrated them into just one standard drive module that would look like any standard VFD, except it's a little larger physically. The other new technology that's available is matrix technology. Full disclosure, I am the product manager for the Yaskawa U1000 matrix drive. This drive is an AC to AC drive. It's the one model on the market that produces a variable frequency, variable voltage output to a motor from an AC power source without the use of a DC bus for power conversion. So in a matrix drive, you have, as the name implies, a matrix of 9 pairs of IGBTs that are arranged in such a way that the 3 input leads to the motor can be connected to a line lead, L1, L2, and L3 at any given point in time. And the technology operates on the principle that if you look at a balanced 3-phase power source, the voltage difference between phase 1 to phase 2 added to the voltage difference between phase 2 to phase 3 equals your total line voltage. So the drive, using very high-speed switching, takes advantage of what I will call a virtual DC bus to use to generate an output to the motor. And with any drive, the nonlinear current draw takes place in the AC to DC conversion on the front end. So by eliminating the DC bus, we essentially eliminate the source of the nonlinear current draw in the first place with the matrix design. And harmonic performance is less than 5% THDI.
Great, that's an awesome overview. So now that we know we've got this toolbox of ways to mitigate harmonics, how do I know when I'm going to run into issues? What ways can I know at the onset of a project, whether it's a new facility or retrofitting a facility, if I even need to be worried about harmonics? And if so, how bad they're going to be and what direction I might need to go for mitigation?
Well, there's a couple of different ways you can go in answering that question. You can purchase a paid harmonic survey. A number of engineering firms will offer these. That would be in the case typically with an existing facility that's looking at an upgrade or an expansion. So you'd want to get an understanding of your existing harmonic status, so to speak, so that if you're adding to the network, what to be mindful of. If it's a new design entirely, there's harmonic estimator tools available that allow you to define your distribution transformer and define, based on the one-line diagram, your drive loads and your across-the-line motor loads connected to that transformer so that you can estimate the harmonic performance of that system. Again, it's an estimation. There's a number of assumptions made, but it can help point you in the right direction in terms of will you have a problem or is your planned system not going to have any issues.
Yeah, and this wouldn't be a Yaskawa podcast if I didn't ask, does Yaskawa have such a tool that people can download for free?
Absolutely, yeah. Yaskawa software tools are, with very few exceptions, offered with no charge, and the Harmonic Estimator tool is one such tool that can be downloaded from yaskawa.com and allow customers to establish their network, the loads connected to their transformer from the one-line diagram. It allows you to pick specific drive models and allows you to actively say, oh, okay, well, my system's non-compliant with standard VFDs, as an example. Let's select a couple of these drives to be matrix drives and see what happens. And then you can rerun the calculations and see the change in impact by adding a low harmonic drive to your project.
I have played with the software, and there's one term I learned that we haven't discussed yet today. So before we wrap up, can you explain what PCC is in case people do come across that term in their harmonics discussions?
PCC, that stands for point of common coupling. And basically that will be the point at which you will establish your harmonics performance calculations. That's the output, so to speak. And in many cases, the point of common coupling is the secondary side of your distribution transformer because that's where your loads all connect to. And at that point, you're looking at the voltage distortion to see just exactly what your other connected devices will see in terms of power quality. But yeah, the point of common coupling, PCC, is an important element to consider when performing your harmonic analysis.
Great, thanks for that. So, as we start to wrap things up here, if you were to kind of summarize our discussion, what would be some of the key takeaways you want to make sure that our listeners remember from our discussion?
Well, number one is that harmonics are the result of nonlinear loads. So a nonlinear load, we covered these earlier, anything with a switching power supply, LED lighting, computer power supplies, EV charging, variable frequency drives are all examples of nonlinear loads. So it's not only VFDs you have to worry about, there's other loads to consider as well that are nonlinear in nature. Also, one thing I didn't talk about is that the size of the nonlinear load has an impact. So, Greg, you may have mentioned this earlier. If a customer has a 1 or a 2 horsepower drive, which in the drive world is pretty small, and there aren't many other nonlinear loads, putting a whole lot of thought into harmonic performance is probably a waste of time. However, if you have hundreds of small drives, they're additive in nature when it comes to nonlinear loads and total power, or you have a small number of very large drives in the hundreds of horsepower, well then, thinking about harmonics and doing an investigation is probably a good use of time. Other factors, transformer size, loading, and the ratio of linear to nonlinear loads on a network are all factors to consider when evaluating an electrical system's harmonic performance.
Jordan, I appreciate that summary and greatly appreciate your time today.
Well, thank you for having me, Greg.
I know this topic can be a scary one, it can be a confusing one, and I'm hoping that what we talked about today, without the aid of visuals, other than our analogies of jumping on lakes and pools, on rafts, was able to give you an idea of what it means when people do mention harmonics. It is important to know that you'd never have to tackle a harmonics situation alone. The manufacturers of the nonlinear loads, such as VFDs, and then of the mitigation systems, such as active and passive filters, all have specialists that can help you, and Yaskawa is no different. Whether it's through line reactors, active front ends, or matrix technology, there's no one-size-fits-all solution, but there is help out there. Big thanks to Jordan for breaking it all down. If you want to learn more, check out Yaskawa's Harmonic Estimator tool, or reach out to our team of application engineers. If you enjoyed today's episode, please like or follow this podcast to stay informed of when new episodes launch. And if we're doing a great job, please leave us a 5-star review. Thanks for joining us, and as always, we'll see you next time on VFD Vibes.